Hi guys, in my previous concept I discussed about resistance which are connected two or three resistance which are connected in series. So in series connection current remains constant and potential difference across each cell will be different. Suppose this is V at first resistance. If the bulb is having resistance R1, V1 is the potential difference across the first bulb, and the second bulb having resistance R2, then potential difference is V2. Then third bulb having resistance R3, then the potential difference across the bulb is V3. In series resistance connection, the total potential difference equal to sum of the individual potential differences. V equal to V1 plus V2 plus V3. And very important point at here, in series, which is constant, in series current I is same, which remains constant. So you can see it here, it is evidence the same charge is flowing all through the circuit. If charge is same, then current remains constant. And we end up by writing V equal to IR. If this I write that series resistance RS equal to I times R1 plus I times R2 plus I times R3. Take the common I and cut it out, and we can write that series resistance RS equal to R1 plus R2 plus R3. So the sum of the resistance is equal to the total resistance equal to sum of the individual resistance. So thus about series resistance. In series, the resistance value will increases. In series connections, the total resistance value increases. And one more observation you need to make it here. So that is, suppose instead of taking its resistance, suppose this bulb having resistance 10 ohms and this is having, let me increase to the 30 ohms. Yeah, let me take it's 30, and let this bulb having as a big resistance which equal to 50 ohms. Now if I can give a supply of let me give a good amount, 45 volts. Oops, I need to connect again at here. If you can give the cell about 50 volts, it is considerable. Now here you can see who is glowing more. Who is glowing more? Obviously you can see the third bulb. Why it is glowing more in the third bulb? What is the reason? If you can see the third bulb resistance, so the third bulb resistance is more than the second bulb, is only 30 ohms than the first bulb. So if the resistance is more, why it is glowing more? So that we can understand that here by relation V equal to IR. In series, who is common? I is common. Current I is common at the first bulb, second bulb and third bulb. If I is common, on the other side resistance increase. So on the left side the potential difference obviously increases. So if I take the help of voltmeter and if we can measure the potential difference across the first bulb, so the potential difference across the first bulb shows about only 5.52 volt. And if we can measure same thing across the third bulb, what do you guess? Increase, decrease, remain same? Yeah, here you can see its value here is showing about of 27.9090 volt. That potential difference increased right here. Ask a question, why the potential difference here need to increase? Why the potential difference here need to increase? Ohm's law tells about it here. The Ohm's law says V equal to IR. If I is common and resistance is more and here equality symbol, obviously the potential difference should be more. It means the bulb at bulb third bulb potential difference, it means it taking more potential. That's the reason, because it requires, why it requires, it's having more resistance. So after observation of this very clearly, now let me take you to another type of combination which is known as parallel combination. So today's class I will discuss about resistance connected in parallel. So you know the meaning of parallel. What is the meaning of parallel? Parallel lines means one upon other like this. Okay, so this connection is known as parallel connection. So let me take bulb. I will take 3 bulbs. So this is bulb 1, second bulb 2 and bulb 3. So these bulbs are having different resistances. So that we know that because the bulb is made up of tungsten filament. So I am connecting a connection wires. So these are made up of copper conducting wires. Now parallel connection means just like all one sides should connect at one point and all other sides should connect other points. So these are the bulb wire connections, and from it here, from each bulb, and we can give to a common connection, means all ends should connect to at one point. So bulb having the 2 ends, all bulbs one end, one terminal is connected to one point and all another ends should connect to another common point. Now if I give across at here, if I take bulb and switch, if I can connect these two, now to the one end, if we connect if we connect the battery negative end, and at another end if we connect the positive end via switch. Now here the switch is off, but this connection we known as parallel connection. See all bulbs are connected in parallel. Now if I switch on, now observe clearly. Here you need to notice 2 junctions. So this point A and this point B. Now what happens at junction A? Current I, if I is flowing at A, from A current is dividing. So through this bulb some charges are the flowing, that I can take I1, and through other some charges are the flowing, that current I2 we take, and through the third one some other charges are flowing, that current we take that I3. Just like water connection, yeah, that you can take an example. So if this is a main canal, so charges at here you convert that into water from main canal. At this junction point, the water is dividing to 3 sub canals, and through the sub canals the water is flowing, and likely when it comes to at here, the same current is flowing through bulb, and same current will becomes at here equal to I1, and here it equal to I2, and from this one it becomes I3. But when it comes to junction B, here you can see the current is adding up. Again at junction B, the total current equal to I. Now at junction A, the current is splitting, I equal to I1, I2 and I3. And at junction B, the same currents are adding. So the total current remains constant throughout the circuit. But through each bulb, in this case, the current value is different. So let us see if we can, what happens if we can increase the voltage. If we increase the voltage, if you can see, all bulbs are the glowing equally. There is no change in the intensity of that one. Suppose let's take these three bulbs are having the resistance R1, both are having 10 ohms, 10 ohms, 10 ohms. And suppose if we can increase this to a fix up to a 10 ohms. Now the potential difference here equal to, let me take, this is a 10 volt, 8 volt is sufficient, and 8 volts the same potential difference is flowing from the bulb, sorry, from the source, 8 volts. So let me check what is the potential difference across each bulb. So if you can check the potential difference across each bulb from the positive to positive, so from the first bulb it is showing 8. I'll write with that this, it is showing 8 volt. From the second bulb, if you can take from the second bulb, it is showing the potential difference. The second bulb also showing the same. It is also 8 volt, the potential difference across. And here you can see the potential difference across the third bulb. It is also showing 8 volt. It is 8 volt. Not only that, if you can measure the potential difference across the junction, if you can measure the potential difference at the junction, means at the two junctions A and B, it is also showing the same. So it is also showing 8 volts. So it is something different like in series. In series, the potential difference changes and current remains constant. But when it comes to parallel, what we have seen at here, in parallel connection, the potential difference is constant across the three resistances or across the three bulbs, but current value changes. I hope you got that meaning. Again I am repeating, in parallel connection the current value changes, but the potential difference value across each bulb remains constant, remains same. But in series, it becomes opposite. In series, current value remains the same, but the potential difference value changes. So in this case, how we can derive the resistance value? So the resistance, the total resistance in parallel connection. Let us try to derive that. So the total resistance in parallel, suppose if I take three resistance, so this is resistance, first resistance, which we can call this as R1, and another resistance which is R2, and third resistance which is R3. If they both are connected in parallel, so you can see the connection how we need to join. So these three are connected in parallel to a cell with a key. So this is positive and this is negative, and if this is the current direction, so at the junction, so this is a junction at point A and this is another junction to point B. The current I is divides here I1 to the second resistance I2 and to the third resistance I3, and the same current when it comes to at here, the same current comes I1 and I2 and I3 the same currents will be added at junction B. Now if R1, R2, R3 are connected in parallel between the 2 points A and B, and let I1, I2, I3 are the currents through the resistance R1 and R2 and R3, then we can write, then total current I equal to sum of the individual currents I1 plus I2 plus I3. So this is the expression for total current. Now from Ohm's law, we know that V equal to IR. This is the standard Ohm's law. From this, what can I write? I equal to V upon R, so that I can write that. Similarly, for the across the first resistance R1, so its voltage becomes V1, which equal to I1 times R1. Similarly, across the second bulb, second resistance V2 equal to I2 times R2 and V3 equal to I3 times R3. Now, so from this, can we calculate the value of I1? So from this I can write that I1 equal to V1 upon R1. So here equal to I2 equal to V2 upon R2, and here equal to I3 equal to V3 upon R3. Now we can substitute all these values at here. So in the place of I can put the value upon V by R. So this we can call R suffix P parallel, which equal to V1 upon R1 plus V2 upon R2 plus V3 upon R3. But we saw that in parallel connection, the potential difference is constant. The potential difference is constant. So this is a very important key, very important point to change the derivation. So the potential difference remains constant. So if potential difference remains constant, I cannot write V1. So I can convert that as V and V2 and V3. So here everything will be changes as I3. Or you can take this as a note, V equal to potential is constant, V1 equal to V2 equal to V3. Since in parallel connection. I hope you do not confuse it here. So if that is the change, so let me change it here too also. V equal to V1, V2, V3 gets changes, and take it out the V common on both sides. V suffix R P parallel equal to, in this side you can pull the V outside, V times R1 plus 1 upon R2 plus 1 upon R3. Now you can cancel the both times potential difference, V gets cancelled. Now the total resistance in parallel R suffix 1 upon Rp equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So this is the formula for total resistance in parallel combination. So how we can apply this into the given circuit? Suppose we are having resistance, so this is a resistance of 2 ohm, so which is connected to a resistance of 1 ohm. They both are connected in parallel to a cell. So calculate total resistance of the circuit. Calculate total resistance of the circuit. Since they both are connected in parallel, so this is parallel connection. So in parallel connection, what is the formula? 1 upon Rp parallel equal to 1 upon R1 plus 1 upon R2. Since here only two resistance, I can write the formula like that. So 1 upon R suffix P parallel resistance equal to 1 upon 2 plus 1 upon 1. So here we need to do a little mathematics. Let us do that. 1 upon R suffix P equal to, so 1 by 2 plus 1, which equal to, if you can do the LCM, this gives to 3 upon 2. Let's do reciprocal. Do reciprocal on both sides. So if we can do reciprocal, so that becomes Rp upon 1. So resistance in parallel upon 1 equal to, this becomes 2 upon 3. So resistance in parallel equal to 2 upon 3. So this is the total resistance 2 upon 3, 2 by 3 ohms. Let us try to do one more in the parallel combination. Calculate total resistance. Calculate total resistance of the circuit. Suppose if three resistances are connected in parallel, now let me take the 3 or equal resistance. So this is the 3 ohms, so this is also 3 ohms and this is also 3 ohms, and they are connected in parallel combination. So we need to find the resultant resistance. What is the total resistance? Since they are connected in parallel, what is the total resistance formula? 1 upon R suffix P equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So 1 upon R suffix P equal to, here 1 by R1 equal to 1 over 3 plus 1 over 3 plus 1 over 3. So let's do simple calculation. So 1 by 3 plus 1 by 3. 1 by 3, it goes to 3 upon 3. Now its value equals to 1. Therefore, the total resistance, if you can do the reciprocal, Rp upon 1, which equal to 1. So finally the total resistance is equal to 1. If you can notice, in parallel combination, the total resistance value is less than the individual resistance. I think you understand that notice, that observation. So here each resistance having resistance of 3 ohms, and that 3 resistance connected in series and in parallel. If 3 are connected in parallel, so what about the total resistance? So now the total resistance value here, it is 1. It means the total resistance value in the parallel combination is decreases. Or you can do one observation. Suppose, compare. Suppose the 3 resistors are connected in series connection this time, not parallel connection. Now 3 resistors are connected in series. This is the 3 ohm, 3 ohm, 3 ohm. Let me give to 10 volt supply. Calculate the total resistance. Total resistance. Total resistance of the circuit. Since it is in series, what the formula shall I write at here? Resistance in series, R suffix S equal to R1 plus R2 plus R3. Now series resistance, you can just sum up 3 ohm plus 3 ohm plus 3 ohm. Now series resistance equal to 9 ohm. Yeah, here you can observe the change. So in series, the total resistance is above the individual resistance value. The total resistance of the circuit in series connection is more than the individual resistance value. Here the individual resistance value is equal to 3 ohm, but the total resistance is equal to 9 ohm. But when we connect the same in parallel, when it comes to parallel connection, now here the parallel connection 3 ohms are connected in the parallel, the total resistance is less than the individual resistance. So if you want to increase the resistance, you are having small resistance, you want to increase more resistance, you need to connect that in series. Or if you can make a shortcut, in series the resistance value increases, but in parallel the resistance value decreases. So we will solve some more problems so that gives a better understanding. So finally, I can give a conclusion. Resistance in series formula R equal to R1 plus R2 plus R3, R series. And resistance in parallel. Resistance in parallel R suffix P equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. So very important point to remember, in series who is constant? Current is constant, I is constant. But in parallel who is constant? Potential difference or voltage is constant. Yeah, this is all about series and parallel connection. So in next lecture we can see some problems. So till now we did not solve any problems. We can solve some good problems that gives better understanding how the resistance value increases and decreases.